Hello everyone. I hope you are all doing great. I miss you very much in the previous period. Today I will start recording this session. It's about the analytic geometry. This is chapter number 8 for my wonderful students in FCT, I'm sorry. This is gonna be the part about the analytic geometry. I know, and you know that about the grading formula, that we have the first midterm and second midterm. The first midterm contribution is 0.4, the second midterm is 0.6, and then there is the final exam for the students who didn't pass mid-1, mid-2, or they want to defend their grades. So you will have to finish this chapter, which is about analytic geometry. One of the beautiful chapters that we will be studying this semester. It's a wonderful chapter, it's really very nice, and it's all about how to apply all the information that you studied starting from the scratch, from the first chapter till the end of chapter 7. So chapter 8 in specific, it's dedicated for the straight line and a plan, and its direct application on the vectors, spaces, on the sub-vector spaces, the orthogonal complements, the position vectors or the direction vectors, and the points that belongs to a sub-vector space or from a vector, from a specific vector space. It's really very simple. I will start with some definitions. That's if I have 2 points in R3, for example, x1, y1, z1, x2, y2, z2. If I need the direction ratio or the vector, the position vector connecting these 2 points, it's really very simple. All I have to do is to get the difference between the coordinates of these 2 points. And voila, I have a vector. So it's really very simple. All I have to do is to fix the direction that I'm going to use in this subtraction formula. So I can say simply x2 minus x1, y2 minus y1 for the second coordinate, z2 minus z1 for the third coordinate. And now I have the vector which connects the 2 points P1 and P2. Actually, it's a position vector parallel actual to the main position vector A1, A2, A3, but it's really very simple and I can get it easily and simply, as you can see. Some students will say, what if I take x1 minus x2, for example? It's not going to make a difference, but the main issue is once you start dealing with the first coordinate, you will have to finish the remaining coordinates with the same formula, same way like so. If I said x2 minus x1, y2 minus y1, z2 minus z1, I will have the 3 components or the 3 coordinates of these 3 components. If I made the vice versa, taking x1 minus x2, y1 minus y2, or z1 minus z2 exactly, I will have also a direction vector, which is simply, it's going to be the same. So this is for OA, A1, A2, A3. So this is mainly the simplest way to get a position vector if you have 2 points and you need to have a direction ratio or a direction vector connecting these 2 points. Really very simple. Okay, I will go now for the symmetric equation of a straight line. If I want to get the set of points connecting a straight line, from the concept of analytic geometry, I will have the vector equation or the symmetric equation, which is really very simple. If I want to do this for a straight line or to get the set of points that, if connected together, will give me a set of points belongs to one straight line, all I need to have is just 2 things. The first of them is a point belongs to the line N, for example, okay, and then I will have to have the direction ratio or the vector or position vector of this straight line. So now and once more, if I need to find an equation of a straight line in R3, for example, I will have to have just only one point belongs to this straight line and a direction ratio or a direction vector in the direction of this straight line. So let's say as the notations A1, A2, and A3 stand for the direction vector of this straight line. And if I have a point P which have x1, x2, let's say y1 and z1 as coordinates of this point, the equation of this straight line will be really very easy. This is the form, or the simplest form from my point of view, for a straight line, which is the symmetric equation, as you can see, or we can call it the vector equation, relative that we have the vector or the position vector involved in this equation. The equation states that for the general point belongs to any straight line, which is xyz, if I have the if I subtract it from the point that's given on the straight line and divided on the vector or direction issue, I will have this symmetric equation. So if I have x1, y1, z1, a1, a2, a3, the symmetric equation of this straight line, it's really very simple, and this is very easy to do, is to get these ratios, which is x minus the coordinate of the point belongs to this straight line, then y minus y1, which is the second coordinate of this point belongs to the straight line, and z minus z1, divided by a1, a2, and a3, which are the coordinates of the direction vector belongs to this straight line. All these ratios are equal to each other. So simply, I can say that it's equal to lambda, which is some constant value, belongs to r. Okay, which is really very simple to use and to deal with. This is the equation, or the symmetric equation, or sometimes called in some textbooks or notations as ours, a vector equation. It's really very simple. What I want you to remember in all times, that the point will be on the denominator and the vector will be on the denominator. This is the equation of a straight line. This is really very important to remember, that I have the point on the denominator and the vector on the denominator for this equation. Okay, this is mainly the equation that I'm telling you about, x1, y1, z1, a1, a2, a3. This is the equation, as I told you. And this is the exact formulation from this equation that we said previously. If I have 2 points, x1, x2, y1, y2, z1, z2, I can get the direction vector, or the direction ratio, and then I can use any of these points on the denominator to express the equation of this straight line. Okay, let's see. If I want to have the symmetric equation of the line passing through or connecting the point P and parallel to this direction vector, or if I want to find a symmetric equation for a straight line with this direction vector and with passing through this point, it's really a piece of cake. All I have to do is to just replace the point, which is, for my case here, it's gonna be a 5, negative of a 6, and 2. And for the direction vector, which is half 2, negative 4 over 3, you can leave it as it is, or I don't like to deal with fractions in the denominator, like all of us. So I can say, let's say, I will multiply these coordinates in 6, for example, just to have nice round figures. So the direction ratio, if I multiply by 6, it's gonna be, for example, okay, so it's gonna be a 6, okay, I'm sorry, if I multiply all the 3 coordinates in 6, so it's gonna be a 3, then 6 times 2, which is gonna be 12, then I will have negative 8, check the algebra with me, please. So 6 times half is gonna be 3, 6 times 2 is gonna be 12, 6 times negative 4 over 3, which is gonna be negative 8. So if I won't write the equation, it's gonna be really very simple. All I have to do is write the direction vector on the denominator, which is, again, once more, it's gonna be a 3, then the 12, then then the negative 8. And for the denominator, which is gonna be really very simple, all I have to do is to replace z1, okay, same way like y1 and x1 with the coordinates of the point, which is gonna be a 5, then plus 6, then minus 2, which is simply the symmetric equation of this straight line. Once more, as I told you, now I can get direction vector, which is, I choose to multiply in 6 just to avoid the fractions that you can see in the coordinates of this direction vector. So multiplying 6 by half is gonna be 3, 6 times 2 is gonna be simply 12, and 6 times minus 4 over 3, which you will end up having a negative 8. Simply, the equation is gonna be exactly like this, replacing the x1, y1, z1 by the coordinates 5, negative 6, and 2, exactly as we saw, and replacing the direction vector a1, a2, a3 by the points 3, 12, and the negative 8. And you have a symmetric equation for expressing this straight line exactly. Now, for the straight line, there is also another very important form that we usually use when we get intersection of this straight line with any other shape that exists in R3. For example, if I want to find the intersection point of this straight line and this plane, what to do? It's really very simple. I will use another form of this equation. The simplest form is to put this equation into parametric equation, which is simply, all I have to do is to make this equation equal to t or lambda. I will use t for the time being because I have a couple of examples on this application. So simply I will get the first ratio and it's equal to t. And try to get x in one side. So simply it's gonna be x minus 5 over 3 equal to t, and y plus 6 over 12 equal to t, and z minus 2 over negative 8 equal to t, which is really very simple. Now, I want you to get x, y, and z in one side. You will have the parametric equation. It's really very simple. All I have to do is to say that x equal to 3t plus a 5. So I made a cross multiplication, then moving negative 5 from the left hand side to the right hand side. In a similar manner, I will have y equal to 12t minus over 6. And in a similar manner, z will equal to negative 8 of t, then plus 2. This is actually the form of the parametric equation. If you take a good look for this problem, you will find the following, that the coordinates that goes for 5, negative over 6, and 2, actually it is the coordinates of the point. And the number that's multiplied, the numbers or the coordinates multiplied by t, in the coordinates of the vector. So it can be written on this form. Now, if I want also, I should have a point and the vector, direction vector. So simply, all I have to do is to get x, y, z minus the point over direction ratio. So this actually explains that I have b1 and b, which is the direction vector, and I have b1 and the b2 for the direction vector of this straight line. So simply, I will have b1, b, the main direction, equal to t times b1 and the b2, and simply on a parametric form, exactly as it was said, I can get the x, which is x1, a1t, and y, y1 plus a2t, and z, which is z1 plus a3 of t, which is exactly like what I told you here in this example, exactly. So, if you remark, once more, this is the coordinates of the points that we are talking about, and these are the coordinates of the direction vector of this straight line. So it's really very simple and very easy to go through it and to do it. So once more, straight line equation, you will need a vector in the direction of the straight line, and just only one point belongs to this straight line. Voila, you will be able to find either the symmetric equation or the parametric equation. Okay, an example on this. Find the parametric equation of the line that passes through A and B. Both of them are points belongs to this straight line. At what point does L intersect the XY plan? This problem is really very important. It expresses for you how to get the equation or to form an equation of a straight line given 2 points, and also how to use the parametric equation in order to get the intersection point between this straight line and a plan of the XY plan. So it's very, very simple. I will do it in 2 times. I will solve it first with you on the whiteboard, then we will go through the slides. So mainly, I will need to have the parametric equation of a straight line L. In order to get the equation of a straight line L, first of all, I will need 1 point. So in order to get the equation of this straight line, it's very, very simple. I will need a point, and for the time being, I have 2 points. I have A and I have B. It's really up to you. Choose any one of them. I will go for A. It's written first, so I will consider A, which is 3, 1, and -2. Number 2, I will get the direction vector of this straight line. How to get the direction vector of a straight line? Simply, I will get the difference between the coordinates of these 2 points. So simply, I will say 3, okay, so it's gonna be 3 minus of a -2, which is gonna be a +2. Then I will take 1 for the second coordinate minus the second coordinate of the point, which is gonna be 7. Then I will go for the third coordinate for the first point, which is -2, then minus -4. So I will have -2 minus of a negative over 4. So now my direction vector is 6, and then it's gonna be a negative over 6, then it's gonna be a 2. It's really very simple. So now if you remark, I will choose just only any point. It can go A or B. So you can write this equation using point A or using point B. Then I will get the direction vector of this straight line, which is simply the difference between the coordinates of these 2 points. So you can go AB or BA, it's really up to you. But once you start with 1 coordinate, you should continue on the same manner. So if I'm going to subtract the coordinates of B from A, so it's gonna be 3 minus a negative over 2, so you will have 3 plus 2, which is 5. Please take care of algebra. As you can see, I can do mistakes exactly like you. So 1 minus 7, so it's gonna be negative over 6, -2 minus a negative over 4, which is 2. Now I have the direction vector. Now I can write the equation of this straight line in a symmetric form or in parametric. I would usually prefer to write the symmetric and then get the parametric. I don't need to memorize all of them, but it's really very simple. So all I have to do is to say x minus 3 equal to y minus a 1 and z plus 2, which is divided by the coordinates of the vector. And that's the vector that I'm using, which is a 5, a negative of a 6, and a 2, as you can see. Now I can put this equation into its symmetric, its parametric form, which is really very simple. All I have to do once more is to let it equal to some constant, t, lambda, whatever, the name you can choose easily. And now I can get each coordinate by itself. So it's gonna be an x equal to a 5t plus 3. For y, it's gonna be y equal to negative 6t plus a 1. And for z, it's gonna be a 2t minus 2. These are the coordinates of, the parametric form of this straight line equation. Similar manner, as I told you, I will need to get the direction vector. So I will choose to say -2 minus 3. It's not that one. It's not from AB, it's BA for this one. So I've taken -2 minus 3, it's okay. 7 minus 1, and -4 of a minus of a -2, and I had exactly almost the same direction vector. All the difference between this one and that one is the negative sign. So if you multiply the negative, it's not gonna be a big deal. Okay, perfect. Then I will start using the equation that I told you about, directly the parametric equation, which states that I will make the point, I will put the point that I choose, 3, 1, -2, and the coordinates of the direction vector in front of a t lambda or whatever, and this is the main formula, x1, a1t, y1, a2t, and so on, and it's a direct substitution. So this is actually the equation that I told you about. Here the coordinates of the vector, and here is the coordinates of the point that I'm using. Now, and for the time being, so for the first part to form the parametric equation connecting A and B, it's correct. Now, at what point does L intersect X and Y? So this is a straight line, which we call it the L line. I need to find the intersection point, the intersection between L and the plane, which is X and Y. The plane X and Y, it's a subvector space from R3, from the language of vector spaces and subvector spaces. Actually, it's all the points and vectors that belongs to the general form of a plane of an XY, and all these points will share the fact that you will have in R3 X value, Y value, but the Z value equal to 0. And this point belongs to R3. Actually, it forms a subvector space from R3. So it is all the points on this form, XY, and the Z equal to 0. So if I want to find the intersection point between this straight line, so let's say this is our plane, okay? This is the XY plane. And if we said that this is our straight line L, so I will need to find the point M, which is actually the intersection between the line and the straight line. How to find this point? So if this L, and this is the plane equation that I'm telling you about. If I want to do so, all I have to do, let's make this like that. So this straight line actually cut this plane or intersect this plane in a point. All I have to do is to see the equation of this plane. The equation, as we will see down the road, of the XY plane is the condition. The condition states that it is the set where Z equal to 0. So if I want to write the span of this vector space, so subvector space actually, it's gonna be the X, it is the set of points, I can write that. This plane is the set of all points, X, Y, and Z, that belongs to R3, such that Z equal to 0, and of course, when you make the substitution, so it's gonna be X and Y and Z equal to 0, and this one is gonna be 1, 1, and 0 for this set of this subvector space. If you like to do it like this way. Simply, I will need to put Z equal to 0 in order to get the equation of the plane of X and Y. So, I will take advantage from this point. That's all the points, or the point that I will need to find, it has Z equal to 0. So all I have to do now is to make the substitution. The magic happens when you put Z equal to 0. So let's put Z equal to 0 in the equation of the straight line. Once more, this is the parametric equation of a straight line. I will take this note and I will use it with the Z coordinate. Just only the Z coordinate, because it is the condition. So it's going to be a 0 equal to a 2 over t minus 2, which is going to lead to 2t equal 2, that's t equal to positive 1. Now I have the condition and I know the value of t, so making a back substitution, knowing the value of t in the equation of the straight line L, I will now have the m value or the point. So substitute t equal to 1, so it's going to be 5 plus 3, that's for the first coordinate, and 1 times negative c is going to be negative 6, plus 1, so it's going to be a negative over 5, 1 once more for the last, so it's going to be a 0, and this is the point that we are seeking. Now once more, exactly as I told you, the line intersects the xy plane, and it's a subvector from R3, with the condition that z equal to 0. So simply all I have to do is to get back to the equation, the parametric equation of this straight line. Inserting z equal to 0, I will have t equal to negative 1. So it's actually working with the specific or compensating with the specific equation that you form. Here I got t equal to positive 1 because I had a vector which is 5, negative 6, and 2. Once you change the vector to be the other side, negative 5, 6, and negative 2, then the t also will be different. But once you use t with this line format, you will have the m exactly as we said, x equal to 8, y negative 5, and the z equal to 0, exactly like what we get. So it's really very simple, same steps, same everything. As you can see, here's 8, negative 5, and 0, exactly like 8, negative 5, and 0. This problem is really very important, and this is the beauty of the analytic geometry. It's connecting everything, equations, understanding of vectors and points, how to use the equation of a straight line, how to use the parametric equation. Once you substitute in a plan, you will get the corresponding points, blah, blah, blah. As you can see, everything works together beautifully. So it's a really very nice application. Here's also a question stressing on the fact that I can write the equation of a straight line, but by plenty of ways, by just replacing the points, replacing the vectors, and so on. So he's stating that get two sets of equation or a vector equation of a straight line connecting these 2 points A and B. So he's stating that let's take A, the point, and let's get a direction ratio which can be easily formatted from, or you can get it by subtracting 6 minus over negative 2, 1 minus 2, 2 minus 4, and you will end up having this direction ratio, which is a 9. 1 minus 2 is going to be negative 1. 2 minus 4 is going to be a negative 2. And I'm using the coordinates of the point. So x minus negative 3, y minus 2, z minus 4. This is for the first equation. For the second one, I can simply get b instead of a. And it's going to be 6, 1, and 2. And also performing for the vector, I've replaced these 2 points. You will have negative 9, 1, and 2. So this equation is exactly similar to this equation. And these are the 2 forms of this symmetric equation, which indicates, as we saw previously, that there is a lot of ways to write an equation of a straight line. Okay, perfect. Now, for the time being, I would like to get back to the main slides. So, before we do so, the summary of these slides. If I want to get an equation of a straight line, I should have just only 2 things. 1 point belongs to this straight line, and a vector in the direction of this straight line. The symmetric equation will be simply x, y, and z minus the point divided by the direction vector of this straight line. That's it. If you want to put it on a parametric form, just to form the symmetric equation, put it 2t, get x, y, z in one side, as I did with you exactly. If you want to memorize directly the parametric equation, it's simply the point, which is x, y, and z, equal to p1, the point on the on your straight line, plus a lambda or a t which belongs to r times the coordinates of the direction ratio or the direction vector that you are dealing with. And that's the parametric equation. I will go through all of this once more, but in our main slides. Okay, exactly as I told you, let's get back to our beloved slides. So I will start exactly as your slides. I sent it to you earlier. To define a straight line, we need 2 points on this straight line, exactly like what we said. Or a point on a line and a vector, that's what I told you about, which is the position vector. A non-zero vector parallel to a straight line R is called the director vector, exactly as we said. So I have a point and a direction vector. If point is A1, A2, A3, and if the point, yes, exactly, A1, A2, A3, and the vector of this equation is given to you. So simply I can write P, which is XYZ, equal to the point belongs to this straight line, plus some constant times mu. And this is the parametric equation that I told you about. Okay, once more, these are the points that we stated previously. I thought it's really very simple just to show you this slide, which is exactly similar to what we did go through exactly seconds ago. This is mainly the point, the direction vector. This is the symmetric or the vector equation. This is the main form of this equation, and in parametric form, just put it equal to a lambda, and you will get the parametric equation. This is the characteristic, the Cartesian, and for the parametric equation, all I have to do is to say that x equal to a1 plus lambda y1, exactly like this one. Y equal to a2 plus lambda times u2, which is exactly like the parametric equation. So mainly point, vector, the point will go the first, then the vector will be multiplied by lambda, which is by the end of the line belongs to an r. So there is also plenty of manipulations if you want to get the values. This is the symmetric equation. I can get it from the parametric by getting lambda, which is equal to x minus a1 over y over u1, same way like for the second component and third component. All of them equal to lambda. This is the symmetric equation or the normal equation of the straight line in R3. Also, I can manipulate it a little bit. So if I take, for example, the last two ratios, which is y minus a2 over u2, z minus a3 over u3, and using advantages, the advantage of reforming this ratio by saying u2 over u3, which is going to equal to y minus a2 divided by z minus a3. So this is mainly going to be the form that we are looking at. If I make this ratio equal to n and make a cross multiplication in order to get the values of u2 over u3 equal to n, and taking advantage of a2 minus n a3, just a multiplication, I will say it's equal to q. I will show you why. Because now I can say that y equal to nz plus q. I have sent to you the details of this slide. Also in general, in the same way like, I can take the first two ratios. So it's going to be u1 over u2 equal x minus a1 divided by y minus a2. And also put it equal to m or n. And then getting x as a function of these two values, call it p. I can reform the equation to be on the reduced equations, which is an x equal to mz plus p and y equal to nz plus q, where m and n is given to you exactly. That's the m value, which is standard for u1 over u3, and the p is a1 minus m times a3. If you like to use these shortcuts, it's okay also. So this is mainly the reduced equation. Once more, I will start from the parametric, getting the symmetric equation, exactly like what we said once more. This is the normal equation. If I take advantage from the first two ratios, u1 over u3, which is m, u2 over u3 equal to m, b is going to be on this form. I've simplified in the previous slide. Q exactly, it's gonna be this ratio, and it was simplified in the previous slide. I will get this reduced equation as you can see. Now, I would like to talk about the plan equation. So, for the time being, it's exactly the same. If I need to get an equation of a straight line, all I have to do is to get a point and the vector, the direction vector of a straight line in its direction. Now, I will talk in specific about the normal equation of a plan. In order to get an equation of a plan, or the normal equation of the plan, it's really very simple and also very close to a straight line. The equation of a plan will require, so once more remember, equation of a straight line, the symmetric equation, you will need a point, don't you ever forget, and the direction vector in the direction of a straight line. Okay, this is the equation of the straight line because they are connected together. And now I'm talking about the equation of a plan. The plan will be mainly written using its normal vector, or the orthogonal complement on all the points belongs to your plan. So mainly, if this is the plan that we need to find, if I have two vectors, or any vectors belongs to it, I will need this normal vector, or the orthogonal complement of this plan. So if we say that once more, this is a normal vector of a plan, so a point and a normal vector on the plan. Okay, this is the normal vector. Okay, so once more, as I told you, I will need a point and I will need the normal vector on the plan. So if I need to write an equation of a plan, it's very, very simple. Also, just only two things. So this is the equation of the plan. Number one, I will need just only one point belongs to this plan. Let's say x1, y1, and z1. This is the point belongs to our plan. And let's say that I know its orthogonal complement or the normal vector on this plan, which I will say a1, a2, and a3. Simply, the equation of this plan, once